So why are we using SSH? SSH is a way to securely get access to a remote computer. So it stands for Secure Shell, and it's a protocol that encrypts and authenticates the communication between you and the remote host. In between can be, for example, the unsecured internet, and you don't want to, for one thing, other people see the data that you transfer to the cluster, see what commands you're typing and so on. But you also don't want to give other people access to the cluster and your data. Therefore, we're using SSH, and OpenSSH is an implementation of these SSH utilities. As we see here, security is important. There are constant attacks on European HPC clusters to get access to the computational resources or get access to the user's data. And then it would be possible to, for example, get access to some user's data and then get some other credentials to get further access to some other cluster and so on. Therefore, it's good to know how to use SSH and how to set it up properly. But first, let's take a quick look at some basics of encryption to get a little bit of understanding how this works. Encryption is the process of converting some information, some plain text, the original information, into this alternative form, the ciphertext, the scrambled form that can't easily be read. And decryption then just reverts this encrypted ciphertext back into the plain text. And the cipher is the method that we use to do this encryption. And for example, we have here this Caesar cipher. It's a classical one, but quite insecure. And it works like this. You get your plain text and you have some kind of encryption key, for example, 17, and this is used as an offset to just move every letter of the plain text in the alphabet. For example, in this case with the -3, an E turns into a B. And we can apply it to the plain text, and then we get our ciphertext. Now, if you want to decrypt it again, turn the ciphertext into plain text, we use the same key, 17, but just move the letters in the opposite direction. And as you can see here, that's not a very good encryption. We can already see some pattern. For example, here the SS of the plain text turns into the JJ, so we already see some information from our plain text, so it's not very secure. And there's the key space is also not very secure. It's easy to crack this. And when we are talking about some encryption, we talk about Alice and Bob that try to communicate, and an attacker that tries to read this communication. Now let's see what happens if, for example, Alice wants to communicate to Bob or vice versa. They want to send messages, and for example, Alice wants to say hello and encrypts it with the key, then sends the message, the encrypted message, over the internet. But now she also has to get the key somehow to Bob. And she would also send it over the internet, and Bob could decrypt it, the message, using the key. But in this case, an attacker that could read all of the communication would have both the message and the key. And in this case, it's basically useless because then the attacker can simply decrypt the message. So this kind of symmetric encryption, where we have one key for encryption and decryption, is not suitable for this case of communication. But there is a different way. There is asymmetric encryption, and it works like this. Instead of one key, we create key pair. And these are mathematically connected. They are generated. And now we can, if we have a message, we can use one part of the key that, for example, we call private key to encrypt something, and then use the other part of the key, the other part of the pair, to decrypt it again. And we can do it also vice versa. We can use the public key to encrypt something and use the private key to decrypt it. And by convention, one part is then called private and the other one public, because the idea is that the private key you keep secure, you do not publish, you do not share, because it's your private part, and the public one, this is the one that you can share to use this encryption scheme. Now, how does it help us? Alice and Bob now can simply generate these key pairs. The private part they keep private, but the public parts they can publish. For example, Alice publishes her public key and Bob has Alice's public key. And now Bob could use this public key to encrypt a message to Alice and send it to her. And Alice has the private key and can use this one to decrypt the message. And an attacker could have the encrypted message and the public key, but this is useless to the attacker because they can't use the public key to decrypt the message. And also the other way around, Alice has Bob's public key and can decrypt a message to Bob using his public key. And in this case, where the attacker only reads the messages, they could use these public keys to create new messages, but that they could send. But in this case, it's not an issue. They can't read the messages of the other people. And this helps us in doing login via public key authentication with SSH. And we will see how this works. Now, in SSH, we have multiple utilities, multiple commands that we will see. We have the SSH server daemon that runs on the remote host that you want to connect to, for example, on our cluster. We have the SSH client that runs on your local machine. And we have some more commands, SCP for copying and for key generation and so on. So SSH is also available on all of the major operating systems and can be used. So we can connect to a remote host, and the first thing that you will see is the message, as we've seen in my demonstration. And this message is a fingerprint hash from the server, and our client shows to us this fingerprint and asks if we are sure that the remote host is really the host that you want to connect to. And this fingerprint is basically hashed version of some cryptographic material from the server. And the first time we don't know anything from the server, so we have to either accept it, and this is called trust on first use, and SSH will write this fingerprint into a local file, and the next time we are logging in, we connect to the server, it compares this stored value with the new value to make sure that it's the same host that we connect to. And the other possibility is to check the fingerprint and compare it with a known list of fingerprint to make sure that it's the real host and not an attacker that sits in between. So this can happen, and then SSH will give us a message and say, okay, this could be a man-in-the-middle attack because someone is in the middle and exchanged this cryptographic material. Or it could be that the server administrator that just reinstalled the server and changed the cryptographic identity of the server. And then we need to enter our password for authentication. And now here is where we can use SSH Public Key Authentication. Instead of using a password to authenticate ourselves to the server, we can use a key pair where the server knows the public key because we tell him when we set this up, and we have a private key and then can cryptographically prove that we are allowed to access the server. For this, we need to generate our public key pair and copy the public part to the server, and then do a little bit, add a little bit in our SSH configuration. And as explained, when we generate the key pair, the private key should be private. So in this course, when you try it, or for example, try it on the cluster system later on, this is for training purposes. If you generate the key, do it on your local computer and then keep the private key secure. Now the first step is to generate the key pair. For this, we are using the SSH keygen command, and here we specify the type of the key and the file. So it's usually stored in your home folder under .ssh and then the name of the key. And you can add a comment. A comment is useful to identify why did you generate the key. And it will ask you to specify a passphrase. This is not your password to the cluster. This is a new passphrase to encrypt the your SSH private key to keep it secure on your computer. And next to the SSH private key, there's also the public key generated under the file name .pub, and this is unencrypted. Next step is to copy your public key to the remote server, because the remote server has to know your public key to do this cryptographic authentication. For this, there is this SSH copy ID command, and you can give it the file path to your public key and then specify to what host it should be copied. And for this step, here again, you see the well-known argument from SSH, your login name and the host name. And you, at this point, still need to enter your password to the cluster because you're still setting up the authentication. And then it will be stored into the .ssh/authorized keys file on the remote host. So SSH copy ID takes care of that. Unfortunately, under Windows, there is no SSH copy ID command, but you can simply add the content of your .pub file to the content of your .ssh authorized keys file on the remote host. So you would need to do it manually. Therefore, use SSH to log in and then open the text file and so on. So the next step would be to add a little configuration in our SSH config to make it more convenient. And this configuration looks like this. You can give it a free name. It doesn't have to be the host name, because the real host name you can specify here. It can be something that is convenient to you. For example, here, user training 001 Otus. It's not the name of a real host. It's just a short alias for you that you can then later use with SSH. And when you later use this alias, then it's using this host name, this login name, and then uses this key for authentication. And then when you're using SSH and then this alias, then you will be asked for your passphrase to decrypt your private key to do the authentication. And then not your password for the cluster is used for authentication, but this public key pair is used for authentication, which is stronger and we can also see that it can also be more convenient, because at this point you just exchanged the password for the cluster to the passphrase of your private key. But if you are often using the SSH command, maybe it's a little bit tedious to always enter your passphrase. And for this, there's also this SSH agent, which is a little program that runs on your local machine and that remembers the decrypted private key. And it works like this. If it's not started, you can check with SSH -add -l to see if it's already running. Often, for example, in normal Linux distributions or macOS, it's already running in the background. But if not, maybe you have to set it up. Also on Windows, you have to first set it up as a service to start at the beginning. But if it's not running and you want to only use it in your current shell, you can run this. Then it will be running in the background. And then you can add a key to the agent. And this will ask for your passphrase. So you have to decrypt your private key so it can be copied into the main memory of your computer. And now afterwards, every time you use SSH here, SSH can ask the agent, do you have already the private key? If yes, then it uses the private key and doesn't ask you for the passphrase. So you don't have to type the passphrase anymore. And if you're done with your session, whatever you wanted to do, you can remove the private key from the agent, or you can also kill the agent. And afterwards, SSH won't find the agent, or the agent will say, okay, I don't have the private key anymore. And SSH will again ask you for the passphrase to decrypt the private key from your home folder. So this makes it a little bit more convenient to use SSH to not always enter your passphrase. Now, we recommend to use different keys for different remote hosts, simply as a security measure. So if for whatever reason one key leaks, then only one host is then can be accessed by the attacker, and not also other hosts that are all then using the same key for authentication. So there is a feature called X11 forwarding in Linux that allows you to start GUI applications on the remote host and then see the window on your local machine. And for this, we recommend, if you want to use it, then only activate it when you really need it on the command line, and else disable it. Because when you are using it, then applications that run on the remote host will be able to access the X11 windows on your local machine. So this is for features, for example, like a screenshot. You want to make a screenshot of a different window, then your screenshot program has to have access to the different window. And this way, then this application that runs on the remote host would have access to your local X server. So we recommend it, usually leave it disabled and only enable it if you want to really use it. So if you don't know anything about this, then this is also fine. This is just optional if you need it. If you're using X11, yes, because then the access is forwarded to the remote host. So don't do it. Only if you need it to. If you need to. So this is the end of this section. Do you at this point have maybe some questions before we go into the hands-on session? Okay, so in this hands-on, maybe you already guessed it, we want you to try to generate a key pair, and you can do it on, for example, the training machine, and then use the jump host as the remote machine to train it. but then, as explained, don't use this generated key because the key was then generated on the remote host, and you usually don't want to do that. So for this training purpose, you can do it with the training machine and the jump host, or with your local machine and the training machine as a remote host, as you wish. Let's see. First things first, let's generate an SSH key pair. So I'm gonna do this with the training machine and the jump host. And so it actually is not that complicated. Once you did it once or twice, it's you will see it's just a few simple steps. Let's call this identity autos, and as a comment PC2 autos cluster, and then ask for a passphrase, and it generated the key. So we can again take a look inside of the .ssh folder, and we see that the private key and the public key were generated. Next step is to copy the key to the remote host, and in my case here, let's see, the public key at the remote host is the jump host in this example. So it asked again for the password, and now it added the public key into the authorized keys file on the cluster. And finally, we can add a config file. So we can ignore this. And let's call it autos cluster, and you see that this is an alias. It's not the real host name. I just, for convenience, named it like this. And just add the real host name, the user name, the identity file, so the path to the private key. This tells SSH to only try to use this key with the server. And now let's see if I try to connect to Oto's cluster. It will ask for the passphrase of my key and not for my password anymore. So if I enter my passphrase, I can connect to the remote host. Now let's also try the agent. And as explained, with SSH add -L, we can check if there's an agent running. And with this command, we can start one and make it available to this shell. So SSH knows how to connect to the agent. So SSH add will also work. Now we see that the agent is running, but it does not have identities, and we can simply give it the path to our private key. And now we see it has this key memorized. And we also see our comment here. And now if I'm using SSH Otus cluster, I don't even need to enter my passphrase anymore. And this also works with SCP because SCP also just uses SSH under the hood. And now I can also remove it again if I'm done with my important work. And we see it, it is gone again. Now if I try again, then SSH asks me again for the passphrase.
What happens if you don't using a passphrase?
So the question is, what happens if you don't use a passphrase to encrypt your private key on your computer? Then your private key will be unencrypted, and everyone who has access to your hard drive would also have access to your private key and then also would be able to authenticate to the remote host. So it would be a good idea to make sure that your private key is encrypted. So in the unfortunate case when you lose your computer and someone has access to the files, then the private key would still have this barrier of protection by encrypting the private key. But this then also depends on how good your passphrase is.